Welcome back. We're doing now the solution of the exercise 9, evaluation of improvements of PV module. So the first question has been an optical one, the optical measure. So we apply anti-reflective coating with a reduced refractive index on the PV module surface that increases the optical transmission energy weighted by 3% over the whole day. First question was, for which parts of the day that measure works most effective, considering a standard installation orientated towards south at a module elevation of 30 degrees Y. Here you see the optical performance over the incidence angle. So you see here the optical transmission, and at the 0 degree of incidence angle you have the best performance. If you go to higher incidence angles, this performance is being reduced. So here you see the effect of the anti-reflective coating. So you don't see such a big difference as perpendicular incidence, but more on higher incidence angles. You can also calculate it mathematically by applying the Fresnel formula. So for larger incidence angle in the morning, evening, the difference becomes bigger. So next question was, does it make economically sense if such a layer costs 10 euro per square meter, the module efficiency of 17%, module costs at 30 cents per watt? What are the maximum extra costs for that measure, considering the upper parameters given? Are there impacts on the balance of system costs? So the anti-reflective coating would make sense if the gain and the related costs would be cheaper than the additional modules which you need to supply that power, offering the same amount of additional electrical energy. So 1 square meter of module costs at standard test conditions, 1 square meter, 1000 watt per square meter. This would generate, because you have a module efficiency of 17%, you would generate about 170 watt electrical under standard test conditions. That PV module of 1 square meter size costs then 170 watts times 0.3 watts under standard test conditions is 51 euro. So an additional 3% of module area we need to generate 3% of extra energy, and that would cost 0.03 times 51, or 3% of 51 euro, that's 1.53 euro. So while our costs are already at 10 euros per square meter, it doesn't make economically sense at all. So the maximum price would make sense with 1.53 euro per square meter, not 10 euro per square meter. Are there impacts on the BOS costs? The RSE does not extend the BOS costs. Contrarily, if you have a bit more power for large-scale applications, you would need 3% less land and less wiring and so on. Last questions of that chapter is, what will be the effect on the electrical output parameters, such as voltage, current and power? So the anti-reflective coating is increasing the number of photons reaching the PN interface in the solar cell, such increasing the number of electrons being generated, and therefore is increasing the current, not the voltage, the current, and accordingly the output power by about 3%. There's no significant impact on the voltage. Voltage may increase very little due to the increased effective irradiance by a little bit reduced weak light effect, but that's neglectable. On the other hand, temperature is increased a little bit, thus reducing voltage very little. Let's come to the thermal measures. So we have a new backsheet with an increased thermal emissivity that reduces the operating cell temperature. And the question is, for which parts of that day that measure works most effective, considering a standard installation, also module orientated south at an elevation angle of 30 degrees. Why is it so? Remember this big formula here from the radiative transfer If you go here to the right side, you see that the emitted power goes up by a power of 4. That's radiation exchange between the module surface and the sky. Here the components what we can influence is the thermal emissivity here, and that's almost linear. So you see a linear relation between the emitted power or the heat flow and the emissivity. So when is the effect the highest? If you go to higher temperature, the more is relatively emitted by thermal radiation. So therefore that measure has the best effect at the highest temperature during day, which is around midday until the afternoon. So it's not symmetrical at midday, so a bit from midday towards the afternoon. So this is about 11 a.m. to 2 p.m. So you saw here, this is the temperature curve around the day. So here 11 to 2 p.m. is the best effect of that measure. Next question is, does it make economically sense? Same values for the new backsheet, 10 euro per square meter, module efficiency 17%, and module costs of 30 cents per watt. What are the maximum possible costs for that measure considering the upper parameters given? So temperature reduction is already energy weighted. Otherwise we would have to calculate power output for each part of the day considering actual irradiance temperature and so on. So we have the power and the energy in this case. The relative increase is delta P divided by P is the relative temperature increase times the temperature coefficient for power, and that's 2 Kelvin. The temperature coefficient is minus 0.5%. So you have got 1% more power. So we have to consider what is this 1% worth. This is about the same calculation as we did before, but we have only got an increase of 1% only. So we have the module costs of 51 euro, and 1% increase is worth 51 euro cent and not 10 euro, or both considering a 1 square meter module. So the maximum price for that backsheet would be a 51 euro cent per square meter. What will be the effect of that in terms of electrical parameters? So a temperature reduction leads to increased voltage and also output power with a negligible reduction in current. So you see this curve, remember this from the very first lectures. So we have here the voltage and here the current. If you go to lower temperatures towards the blue lines, you increase here the open circuit as well as the voltage in maximum power point. You decrease the current, but just a little bit. So the main effect is the increase in power output due to temperature reduction. Here you have the coefficient, which was in vicinity of minus 0.44 per Kelvin. At temperature increase, power decrease. So we come to the very last measure. So that's the application of a phase change material on the back surface of the module. So this would extend the lifetime by 5 years. It increases temperature by 3 degrees. First question is, what effect do you expect during the course of the day, considering also a standard installation orientated towards south and an elevation angle of 30 degrees? So due to the reduced thermal conductivity, we would have here voltage is reduced and also power output is reduced, but linearly. So as you see here, this curve and this constant coefficient. And so we would have here for 3 degrees of temperature increase, we will have a power loss of minus 1.5%. So the PCM is reducing temperature as long as the PCM is still melting. So then we got more power. This happens in the morning when all material is molten. Then the PCM doesn't have a positive effect anymore. It even will increase the temperature due to the reduced heat transfer, while this material has a higher thermal resistance. And this happens in the afternoon. So let's do an economic evaluation. So temperature increase is already energy weighted. We have here the power, and the energy is decreased by minus 1.5%. But we got an extension of lifetime, which is 5 years. So instead of 25 years, we got 30 years. So that's a plus of 20%. So considering the additional thermal losses, in total we still got 18.5% in gain. So it would make sense if that backsheet or the PCM backsheet would be cheaper than the mentioned 10 euro per square meter. So this would lead, if you got an 18.5% increase, so that is, the value of that is 9.1 euro. So that's very close to the break-even point of 10 euro per square meter, but it doesn't make economically sense yet. So again, what will be the effect on the electrical output parameters? Speaking voltage, current and power. In the morning, the PCM reduces cell temperature as long as the PCM is still melting, so we get more voltage and more power and a negligible reduction in current. In the afternoon, when all material is molten, PCM have no use anymore, it increases even temperature and therefore also decreases voltage. And therefore we've got some power loss, which you see here. So this is, the colored lines are the gain in power in the morning. The yellow line, by the way, is the irradiance there. So as you see here, midday, but while we have summertime, it's 1 p.m. And when all the material is molten in the afternoon, then we don't have any gain, but losses. So the main effect is here the extension of lifetime only. That's it. Thank you very much.